Hello everyone. So I welcome you once again in my lecture, and today we are going to talk about tree. Tree is a very important data structure and it's a very important concept in computer science. Tree is used in many applications for implementation. Tree is used for searching, like we have binary search tree for efficient searching. We have we are also using tree for sorting, like heap sort. So heap is again a tree which provides a sorting of a given sequence, and it's shorts in n log n time, which is assumed to be a efficient running time for any sorting. It is also used in databases widely for indexing purpose. So with the help of this concept, we are able to make indexes so that the database can be stored and retrieved efficiently. It is also used for routing purposes. So we are having a modern routing technique which is actually using tree methods. So tree is very important for implementing many of the applications. So in this lecture we are going to discuss and understand what actually the tree is and how we can use this concept to implement different applications that we are using in our day-to-day life. So let's start. So let us look to the formal definition. So tree is recursively defined as a set of one or more nodes where one node is designated as a root. So tree is a collection of elements where each element we are calling as a node, and out of these all elements we have a special node we are calling as a root. So if you look at this figure is representing a tree, and one thing to note here, that in the real life when we talk about the tree is something where the root is at the bottom and then it moves towards up. So tree is something looks like us in the real life where the root is at the bottom. But when we talk about the tree in context of programming, in context of computer science, then the root is actually exist at the top. So here this is the root and then it goes downwards. So instead of moving to upwards, our tree moves downwards. So here it is a collection of elements, let's say R1, let's say N1, N2, N3, and 4. These elements are said to be our nodes, and out of all these nodes, one node is a special and is called said to be a root. So here you can see all these A, B, C, D are the nodes of this tree, and this is a special node and we are calling it as a root. So one node is actually the special we are calling as a root, and other nodes can be partitioned into the non-empty set, each of which is a subtree of the root. So here out of all the given nodes, this is a special node we are calling it as a root, and then other nodes we are calling we are collectively calling it as a subtree. So if you look at this structure, this is one set which is a subtree of this node. This is again a set of nodes which is again a subtree of this root node, and this is again a subset of this node, and this is a subtree of this node. So here you can see that uh, for this entire figure, this is one tree where this is acting as a root and these are acting as a subtree. Again in the subtree we have a dedicated node, we are calling it as a root of that tree. So here you can see that this is how the things are actually worked and how we are going to refer the tree in data structures. We have many terms that we use with the tree. So when we refer the tree, we are going to use these terms. So these are the important terminology that is being used with the tree. So the very first thing is the root. Already we have discussed that root is something which is a special node. Now here you can see when we talk about the tree, we have a node and then they are represented like this in this format, and we are calling this as a root node which is at the top, and then these down nodes are having one relationship. So if I say this node, then this node is actually the parent of this. So if I give the name here A, B and C, then B is a child of A, C is a child of A, or you can say A is a parent of B and C. So if you find any node which don't have any parent, then that node is said to be a root node. So you can see here this is a node where we don't have any parent, so this is a root node, while all other nodes are having a parent. Siblings are the nodes which have the same parent. So if you look at this node B, C and D, these nodes are having a same parents. So these B, C, D are said to be a sibling. Similarly, G and H are said to be sibling, and E and F are said to be the sibling nodes because here E and F is having a same parent. Then we have something called internal nodes. So internal node is a node which has at least one child. So if you look at this figure, here we are using two colors, the blue and green. So blue colors nodes are actually the internal nodes. So if you see here, the blue is our internal nodes. And why they are internal? Because these nodes are having at least one child. So if you look at A, here we have three child, that means it has at least one child. But if you look at this node does not have any child, this node does not have any child. So all these green color nodes are not internal node, but A, B, C and F are internal node, and these green color nodes in this diagram is external node. So external node is a node who don't have any child, and we are also calling it as a leaf. So here you can see that external node is also known as leaf, and these are the nodes who does not have any child. Then we have something called ancestors. So ancestor is the same meaning that we are using in the real life. So if you look at any node, then all the node which appears at the top of that node is actually the ancestor of that given node. For example, here the ancestor of B is A, the ancestor of F is B and A, and we can also give the name to the relationship. So this ancestor is said to be a parent, and this ancestor is said to be a grandparent of F. Similarly, if I look to this node K, then this becomes the parent, this becomes the grandparent, this becomes the grand-grandparent, and all these are the ancestors. So ancestors means all the nodes that appears the top of that node are the ancestors. Descendant is just an opposite of this concept. So all the node that appears down to the given node is said to be a descendant. For example, the descendant of this node is this, this and this, and again this is also the descendant, and again we have a relationship that C is a child of A and G is a grandchild of A and D is a child of A. So these are all descendants. So if you find a node which are connected and appears down to that node, then the then these type of nodes are said to be the descendant. Then we have something called depth. Now depth of a node is a number of ancestors. So if you are asked what is the depth, then you can just find out how many ancestors of that nodes are existing, and that defines the depth. This is one way of finding out. Just find out how many ancestors are existing, or you can find out how many edges are existing to reach to the root. So if I want to know what is the depth of this, I will find how many edges are existing to reach to the root. So I have 1 and 2, so the depth of this is 2. And other way of finding the depth, I can see how many ancestors are there, so 1 and 2, so the depth of this G is 2. Similarly, if I find the depth of I will find how many edges are there, so 1, 2 and 3. So this I is having a depth 3. Other way of finding the depth is you look how many ancestors for this node exist. So this is 1, 2 and 3. So the depth of I is 3. Then we have concept called height. So height, you may find sometimes it is used interchangeably, but the significance of height is different. So height we can find out by looking the relationship of the root and the leaves. What does that mean? It means height refers to the distance of the root to the leaf, or you can say the maximum distance from the root to the leaf, or you can say the maximum number of edges that exist from the root to the leaf defines the height. So if I want to know what is the height of this, so I need to reach to the leaf from this node, and I need to find out how many edges I need to use. So I am going to use one edge, two edge I can reach to the leaf. The other possible way is 1, 2, 3, and the definition is the maximum number of edges required to reach to the leaf is said to be the height. So out of these two possibilities, this is the maximum value, so the height of this node is 3. Similarly, if I want to know what is the height of B, so you have to find how many edges I need to use to reach to the leaf. So this is one way, one edge, two edge I can reach to the leaf, or 1 and 2 I can reach to the leaf, and 1. So we are looking for the maximum number of edges, so the height of this is 2 and the height of this is 0. So the height of any leaf is always be 0. The height of the tree is actually the height of the root. So whenever it is asked what is the height of the tree, then you need to simply look at the height of the root, and that defines the height of the tree. Then we have something called degree. Degree of a node, the number of its children. So you need to find out how many child of that node exist, and that defines the degree. So if I talk about this node, I need to check how many child of this node exist. So 1, 2 and 3. So the degree of this node is 3. As we know that the leaves don't have any child, so the degree of leaf nodes are always 0. The degree of this node, let us check. So this node has 2 child, 1 and 2. So the degree of this node is 2. So degree can be find out by counting the number of child that node has possessing. Degree of the tree is again defined in terms of finding the degree of the node, degree of the root. So if I say what is the height of the tree, you just check what is the height of the root. If I say what is the degree of the tree, then you will just check what is the degree of the root. Subtree refers to the tree that consists of a node and its descendant. So if I say what is a subtree of this node, then you can look to this child, and the entire descendant is actually forms a subtree of A. Similarly, if I want to know what is the subtree of C, you just look to the descendant and we have this. So this is the subtree of C. If I want to know what is the subtree of B, then this is the subtree of B. Empty tree is a tree which does not contain any node. So initially when you start implementing, when you start working it, initially your tree is empty, and we are calling it as a null tree or empty tree, a tree without any node. Then we have term called root tree. So when there is only one node present in the tree, then that time it is said to be a root tree. Okay, so these are the important terms which are often used when we talk about tree. Now let us see that how these terms can be used when we talk about more about the tree.